Hello and welcome to this video. We had covered up to numeric types in the last video. If you see this, we had covered up to numeric types. Now we will study monetary types and character types. Let's see how much we can go up to. So let me bring it to full screen and then we will go. So as you know that I've been going through the SQL language or the data types of PostgreSQL. So it is the continuation of that. So without further ado, let's get started. The money type stores a currency amount with a fixed fractional precision. The fractional precision is determined by the database's LC monetary setting. The range shown in the table assumes there are two fractional digits. Input is accepted in a variety of formats, including integer and floating point literals, as well as typical currency formatting such as $1, 1000, 000.00. Output is generally in the latter form, but depends on the locale. So we have money here. That is the type of name of the type. It takes 8 bytes, stores currency amounts, and the range is given here. So since the output of this type is locale sensitive, it might not work to load money data into a database that has a different setting of LC underscore monetary. To avoid problems before restoring a dump into a new database, make sure LC underscore monetary has the same or equivalent value as in the database that was dumped. Values of the numeric int and big int data types can be cast to money. Conversion from the real and double precision types can be done by casting to numeric first. For example, select 12.34 float 8 numeric money. So in this case, a float 8 data was casted to numeric, which then casted to money. However, this is not recommended. Floating point number should not be used to handle money due to potential for rounding errors. A money value can be cast to numeric without loss of precision. Conversion to other types could potentially lose precision and must also be done in 2 stages. The reason for numeric to work is that it does not lose precision, it is very accurate. So, for example, if you select 52,093.89, which is money, you cast it in numeric to float 8. Division of a money value by an integer value is performed with truncation of the fractional part towards 0. To get a rounded result, divide by a floating point value or cast money value to a numeric before dividing and back to money afterward. The latter is preferable to avoid risking precision loss. When a money value is divided by another money value, the result is double precision, that is a pure number, not money. The currency units cancel each other out in the division. Now we have character types. So there are 4 types here: character varying n, varchar n, the variable length character type with the limit character n, that is char n or bp char n, fixed length blank padded character, bp char, that is variable unlimited length blank trimmed, text variable unlimited length. SQL defines 2 primary character types, character varying and character n, where n is a positive integer. Both of these types can store string up to n characters, not bytes in length. An attempt to store a longer string into a column of these types will result in an error unless the excess characters are all spaces, in which case the string will be truncated to the maximum length. This somewhat bizarre exception is required by the SQL standard. However, if one explicitly casts a value to character varying n or n, then an overlength value will be truncated to n characters without raising an error. This too is required by the SQL standard. If the string to be sorted is shorter than the declared length, values of type character will be space padded. Values of type character varying will simply store the shorter string. In addition, PostgreSQL provides the text type, which stores strings of any length. Although the text type is not in the SQL standard, several other SQL database management systems have it as well. Text is a PostgreSQL's native string data type, in that most built-in functions operating on strings are declared to take or return text, not character varying. For many purposes, character varying acts as though it were a domain over text. The type name varchar is an alias for character varying, while bpchar with length specifier and char are aliases for character. The varchar and char aliases are defined in the SQL standard. bpchar is a PostgreSQL extension. Note that it is an extension, so you have to enable it. If specify, not necessarily, it you may not need an extension. I'm not sure about bpchar, never used it. If specified, the length n must be greater than 0 and cannot exceed 10,485,760. If character varying or varchar is used without length specifier, the types accepts strings of any length. If bpchar lacks a length specifier, it also accepts strings of any length, but trailing spaces are semantically insignificant. If character or char take lacks a specifier, it is equivalent to character 1. Values of type character are physically padded with spaces to the specified width and are stored and displayed that way. However, trailing spaces are treated as semantically insignificant and disregarded when comparing two values of type character. In collations where white space is significant, this behavior can produce unexpected results. For example, select A space colon colon char to collate C less than E, and then within quotes A slash N colon colon char to returns true. Okay. Even though C locale would consider a space to be greater than a new line. Trailing spaces are removed when converting a character value to one of the other string types. Note that trailing spaces are semantically insignificant in character varying and text values, and when using pattern matching, that is like and regular expressions. The characters that can be stored in any of these types are determined by the database character set, which is selected when the database is created. Regardless of the specific character set, the character with code 0, sometimes called null, cannot be stored. For more information, refer to section 23.3. The storage requirement for a short string up to 126 byte is 1 byte plus the actual string, which includes the space padding in case of character. Longer strings have 4 bytes of overhead instead of 1. Long strings are composed by the system automatically, so the physical requirement on disk might be less. Very long values are also stored in background tables so that they do not interfere with rapid access to shorter column values. In any case, the longest possible character string that can be stored is about 1 GB. The maximum value that will be allowed for n in the data type declaration is less than that. It wouldn't be useful to change this because with multi-byte characters, encodings, the number of characters and the bytes can be quite different. If you desire to store long strings with no specific upper limit, use text or character varying without a length specifier rather than making up an arbitrary length limit. So the idea in all this is that if you want, what we can learn is if you want a type which has no length limit, then use either varchar without a length specifier or text. That is the important take from this section. There is no performance difference between these three types apart from the increased storage space when using a blank padded type and a few extra CPU cycles to check the length when storing into a length constraint column. While character n has performance advantages in some other database systems, there is no such advantage in PostgreSQL. In fact, character n is usually the slowest of the three because of its additional storage costs. In most situations, text or varchar should be used instead. So, section 4.1.2.1 has information about syntax of string literals, and 9 contains information about operators and functions. So for example, we have here a table test1 where the column name is A and its type is character 4. So we insert into test1 values OK. And then we select A comma char length A from test1. So A is OK and char length is 2. We then create a table 2 with column B varchar with the limit 5 and we insert OK, good, too long, and so it says value too long for the type is too long for this character varying 5, and then insert into test2 values too long colon colon varchar 5, explicit truncation here. So too long becomes 2 space L, so that is 5 characters, and on selection it gives us OK of length 2, good of length 5, and there are spaces here, so it will take 1 space, and then 2 space L with length 5. There are two other fixed length character types in PostgreSQL shown in table 8.5. These are not intended for general purpose use, only for use in the internal system catalogs. The name type is used to store identifiers. Its length is currently defined as 64 bytes, 63 usable characters plus terminator, but should be referenced using the constant name data len in C source code. The length is set at compile time and is therefore adjustable for special cases. The default maximum length might change in a future release. So this is the information about char length function. The type char is different from char1 in that it only uses 1 byte of storage and therefore can only store a single ASCII character. It is used in the system catalogs as the simplistic enumeration type. So here we have the special character type, char and name. So Uh, when we talk of name, this is the name of the column. So here the name data line is used. So the identifier A, B, C, A and B are the identifiers here. So name represents the identifier. So you see here the name data type is used to store identifiers. Okay. So be careful when you are giving very long column names for a type. Now we have binary data types. The byte array, byte A is byte array data type allows storage of binary strings. So the storage size is 1 or 4 bytes plus the actual binary string and is a variable length binary string. A binary string is a sequence of octets or bytes. Binary strings are distinguishable from character strings in two ways. First, binary strings specifically allow storing octets of values zeros and other non-printable octets, usually octets outside the decimal range 32 to 126. Character strings disallow zero octets and also disallow any other octet values and sequences of octet values that are invalid according to the database's selected character set encoding. Second, operations on binary string processes the actual types where the processing of character strings depend on the locale settings. In short, binary strings are appropriate for storing data that the programmer thinks of as raw bytes, whereas character strings are appropriated for storing text. The byte array type supports two formats for input and output, hex format and PostgreSQL's historical escape format. Both of these are always accepted on input. The output format depends on the configuration parameter byte array underscore output. The default is hex. Note that the hex format was introduced in PostgreSQL 9 earlier versions and some tools don't understand it. The SQL standard defines a different binary string type called blob or binary large object. The input format is different from byte array, but the provided function operators are mostly the same. So we have byte a hex format. The hex format encodes binary data as 2 hexadecimal digits per byte. Most significant nibble first. Nibble is 4 characters. The entire string is preceded by the sequence \x to distinguish it from the escape format. In some context, the initial backslash may be needed to escape by doubling it. For input, the hexadecimal digits can be either upper or lowercase, and white space is permitted between digit pairs, but not within a digit pairs nor in starting \x sequence. The hex format is compatible with a wide range of external applications and protocols and tends to be faster to convert than the escape format, so it's usually preferred. So for example, we have defined the output format as hex, and then we select \x DA AD BEEF as byte array. So that's the output of this. Now we will skip byte array escape format. We don't need to go through this. It is uh, starting from PostgreSQL 10 onwards. So we have hex format. So we'll skip this. Then we have date and time types. Let's see how big is this. Okay. I think we can cover this. It's a bit big. Okay, let's cover it. Date and time types. Okay. Instead of date and time type, I'm thinking of covering the escape format itself and then we will end it. The escape format is the traditional PostgreSQL format for byte array type. It takes the approach of representing a binary string as a sequence of ASCII characters while converting those bytes that cannot be represented as an ASCII character into special escape sequences. If from the point of view of the application, representing bytes as characters makes sense, then this representation can be convenient. But in practice, it is usually confusing because it fudges up the distinction between binary strings and character strings, and also the particular escape mechanism that was chosen to some is somewhat unwieldy. Therefore, this format should properly be avoided for most new applications. When entering byte array values in escape format, octets of certain values must be escaped, while all octets value can be escaped. In general, to escape an octet, convert it to its 3-digit octal value and precede it by a backslash. Backslash itself, octet decimal value 92, can alternatively be represented by double backslashes. Table 8.7 shows the characters that must be escaped and gives the alternative escape sequences when applicable. So if the octet value is 0, then it is 0 octet and it should be represented as backslash triple 0. If it is 39, which is single quote, then it should be backslash 047 in octal. If it is 92, that is backslash, then double backslash or backslash 134. 0 to 31 and 127 to 255. These are non-printable octets and these should be backslash xxx where these are octal values of this. So for example, backslash 001 colon byte array. The requirement to escape non-printable octets vary depending on locale setting. In some instances, you can get away with leaving them unscaped. The reason that single quotes must be doubled as shown in table this is that this is true for any string literal in an SQL command. The generic string literal parser consumes the outermost single quotes and reduces any pair of single quotes to one data character. What the byte array input function sees is just one single quote, which it treats as a plain data character. However, the byte array input function treats backslashes as special and the other behaviors as shown in table 8.7 are implemented by that function. In some context, backslashes must be doubled compared to what is shown above because the generic string literal parser will also reduce pairs of backslashes to one data character. Byte array octets are output in hex format by default. If you change the byte array output to escape, non-printable octets are converted to their equivalent 3-digit octal values and preceded by one backslash. Most printable octets are output by their standard representation in the client character set. So here we have changed the byte array output to escape and then we select ABC backslash 153 backslash 154 backslash 155 backslash 052 backslash 251 backslash 124. So you see ABC is there and then 153, 154, 155 in octal is equivalent to KLM. 52 is star and 251 is 251 and then 124 is T. So here again we have the same information here which we had for output to escape. So depending on the front end to PostgreSQL you use, you might have additional work to do in terms of escaping and unscaping byte array strings. For example, you might have to escape line feeds and carriage returns if your interface automatically translates these. So with this, we come to the end of this video and we have a lot of material to cover with. So we have covered up to 8.4 and we have to go up to 8.21. So there is a lot of material to be covered and slowly we will get there. So have patience because to understand everything, we have to read through everything and then we understand that. So it will take time, have patience. Once all these types are covered, I will show examples of how we can make use of them. For example, in the next video, I might show examples of numeric, monetary, character, and binary data types. Or maybe once we cover everything, then I will show the examples. So stay tuned for more content. Thanks a lot for watching. Happy programming.